EDX Mechanics 1, Mechanics Basic Principles, Modelling in Mechanics. Here's a classic maths problem. If it takes 2 men 2 days to dig a hole 2 meters deep, how long do you think it will take 8 men to dig a hole 4 meters deep? If you can pause the video, you might like to see what answer you come up with. So as a classic proportionality problem, you may have come up with the answer 1 day. However, there's more to the problem now than first impressions. Why could this be considered modelling? And what assumptions do you need to make? So if you think about the actual reality of this scenario, it is actually a modelling problem. What would the reality be compared to the problem you were given? And what assumptions might you make to simplify the problem? So making assumptions or simplifications is a key part of the modelling in mechanics. For example, in this problem we might assume that 8 men can dig a hole at the same time. They can all fit inside the hole. The depth of the hole does not affect the rate at which men can work or dig, and all 8 men will dig at the same rate at all times, and that the earth material is consistent at any depth, etc. And these assumptions, these kind of assumptions, will be increasingly important in mechanics. So for example, what might we assume about the earth when if we were modelling a falling object? So we might assume that the earth can be treated as a flat surface for a falling apple, for example. However, what might we assume about the earth if we were going to model the orbit of a satellite? In this kind of scenario or problem, we might assume that the earth can be treated as a circle if we're talking about orbiting objects. What could we assume about the earth if we're going to model weather forecasts, for example? If we're looking at weather forecasts and temperature changes across the planet, we might assume that it is a sphere for weather and temperature changes, etc. What might we assume about the earth if we're modelling its orbit around the sun? The simplest model or assumption might be to assume that it is a particle in comparison to the huge size of the sun. So all of these assumptions are convenient ways of simplifying the earth in the context of the question. So here we have a problem. We're going to watch a video in a moment of somebody dropping a boulder down a well. You'll hear the boulder hit the sides once or twice, but you should eventually hear the boulder hit the bottom of this hole. And the question is, do we think this hole is 1,500 feet deep?
Good.
So 3 things we might be interested in here. Do we think the hole is 1,500 feet deep? How could we calculate its depth? And most important at this stage is what simplifying assumptions could we make? The first thing I would want to do here would be to convert this into the SI unit of meters. So converting 1,500 feet into meters, we would get 450 meters. So converting this into meters, do we think this hole is 450 meters deep? Before we look at the maths behind solving a problem like this, let's focus on the assumptions. What might we need to assume about that problem that we've just watched? Some of the key assumptions we might make are that the motion is vertical because of the large distance involved. The block can be treated as a particle relative to the deep hole. There is no air resistance, and that the motion is under the effect of gravity alone, and that there's no water in the shaft, and therefore the acceleration is constant. So these are key simplifications to the problem. And, perhaps most important of all, we need to deal with the problem of what about the time it takes for the sound to travel up from the impact back to us at the surface. That is a really important part of the modelling process. So, a nice simple look at the modelling cycle. In the top left corner here, we're looking at defining the problem. You need to understand the problem and define the problem. You need to make simplifying assumptions in order to create a mathematical model that we can solve. Once we have a mathematical model that we can work with, we need to use correct analysis in order to come up with a solution. Once we've solved the model, it's really important to look at the results, interpret the results, and check the validity of the results. Often, having looked at the results and interpreted them, we might need to go back to the problem and redefine our assumptions and the starting point in order to remodel the problem. So there are many common assumptions that crop up in mechanics. Can you see what these assumptions imply in the question? So treating the object as a particle implies the object's dimensions are relatively small. Starting from rest implies that the initial velocity is 0. We're dealing with smooth surfaces implies there's no friction as the objects slide over each other. Smooth pulleys, the implication is that we will have the same tension pulling at both ends of the string connecting the objects together. Inextensible string has the implication that the two connected objects will be moving at the same speed. In the next session, we'll be looking at forces in mechanics.